Hello and good day. My name is SUHANT Raj and my message number is MA23103. So the QC tool I have chosen is control chart. So let's move on. So what we will learn in this video today: the definition and purpose of control charts, types of control charts and the application, how to interpret control charts patterns, and the implementation strategies for quality improvement. What are control charts? It is also known as SUHANT charts. Powerful graphical tools that enable us to study how a process changes over time. Why use statistical process control (SPC)? Tools and procedures can help us monitor process behavior, discover issues in internal systems, and find solutions for production issues. The benefits of this are early detection of process changes, reduce variation and waste, improve quality consistency, da- data decision making. So moving on to the historical background, Walter Schuhart's innovation, where he developed these charts in Bell Labs, introduced the concept of statistical control, distinguish between common and special causes. Evolution to modern SPC, adapted by Japanese industry in the 1950s, integrated into system methodology, digital transformation into real-time monitoring. Next are the type of control charts. There are two: variable charts, which consist of continuous data, and attribute chart, which consists of discrete data. First, we talk about the variable charts. For X and R, it is used for 2 to 8 sample size, between 2 to 8. For the X bar and S, for sample size more than 8. IMR for individual data. Moving on to the attribute chart, P is for proper defect rate, and P num defect items. C count defects, total U count per unit. Moving on to X bar and R charts, which are the most common variable control chart. It is used to monitor the process performance of continuous data, and it is an example of statistical process control (SPC). When to use these charts? When the subgroup sizes are between 2 to 8, continuous measurement data, 1 to monitor both average and variation. Applications are during manufacturing dimensions, temperature control, and cycle times. These are examples of X bar and R chart. Moving on how to select a chart. First, we need to know what is measurement or count rate. We'll focus on the measurements one first, which are maybe length, weight, temperature, time. How is data collected? How many is it? Some groups, numbers between 2 to 8, or individuals where the size is 1. Sample size less than 8, we use X bar minus I. More than 8, we use X bar minus S. For the individuals, we use IMR. Moving on to count rates. What are we counting? Effective items or defects? Items, constant sample? Yes, we use NP. No, we use P. For the defects, which in bracket flaws, constant sample? Yes, we use C. No, we use U. This is a table for the chart type. I'm sorry the table looks like this, but the slide later will actually show a proper table. Well, I'll just say it here. Upper control limit UCAL for the X chart, X bar plus A to R bar. For the LCL, is the same, and the center line will be X bar. For the R chart, the UCL is D4 R bar, LCL D3 R bar, center line is R bar. For P chart, P bar plus 3 in square root P bar in bracket 1 minus P bar over N bracket closes. So it's a quite complicated form. Yep, that's it. So the center line is P bar. Moving on. So the subgroup sizes, the 2, 3, 4, 5, 6 supposed to be vertical or horizontal. So it will be for number 2, A2 is 1.88, D3 is 0. And the D3 for everything is 0, by the way. So key application of subgroup size 2 is small batches, paired samples. For number 3, quality triage samples. For number 4, standard QC samples. Number 5, most common industrial use. Number 6, and is standard sampling. Special versus common cause variation. Understanding process variation. Common cause inherent in the process. Random, predictable statistically. Process is in control. Special cause assignable variation due to specific identifiable factors. Unpredictable requires investigation. Process is out of control. These are the types of variation: common cause and special cause. Implementation steps. First, you need to define the process, then collect data, then calculate limits, UCL, LCL, plot the chart for visual display, interpret results using pattern analysis, signal detection, and identify trend. Next, you have to take action, investigate signal, implement solutions, and update procedures. This is the DMAIC methodology: define, measure, analyze, implement, control. Real-world application of control charts in manufacturing, dimensional control in automotive parts, chemical process monitoring, and food safety parameters. In the healthcare, infection rates monitoring, patient wait times, medication error checking. For service industries, call center response times, order processing accuracy, and customer satisfaction scores. Technology integration. Modern SPC tools, control charts provide visual insights into production anomalies, enabling timely actions. Digital advantages. Real-time data collection, automated chart generation, alert systems for out-of-control conditions, and historical data analysis.